The next set of reactions to talk about are the reductions of carboxylic acids and carboxylic acid derivatives. Overall, there are a few reagents that we can use for these reactions, but there will be two primary reagents that we use. The common reducing agents that we'll see are lithium aluminum hydride and sodium borohydride. Now, lithium aluminum hydride is the first reagent that we're going to talk about, and this is our strong reducing agent. That means that lithium aluminum hydride will reduce everything. It will reduce the most reactive compounds to the most unreactive compounds. Everything gets reduced by lithium aluminum hydride. When we're looking at our reducing agents, this is the structure of lithium aluminum hydride. And what this structure is that it is a source of H-. And H- is a hydride ion that can act as a nucleophile. So just like we've seen a number of other components act as nucleophiles in reaction, this is a reagent that allows H- to act as a nucleophile. Sodium borohydride is our other common reducing agent that we will see. Its chemical formula is NaBH4, and this is our weak reducing agent. That means that this compound is only going to reduce the most reactive functional groups. Compounds that are not as reactive will not undergo any sort of reaction with sodium borohydride. Just like lithium aluminum hydride, sodium borohydride is also a source of H-. Let's start with the reaction of the ester that you see down below. So reaction number 2. If we take an ester like this one here, and we treat it with our strong reducing agent, like lithium aluminum hydride, we're going to have an acid workup at the end of the reaction. The product of our reaction is going to be 2 primary alcohols. You see that the carbons from the carbonyl portion of the ester give us one of our primary alcohols, and then the carbons from the alkyl group on the other side of the ester give us our other primary alcohol. Let's look at this ester. So if we have this ester encounter an aluminum hydride ion, my aluminum hydride ion can act as a source of H- and send that hydrogen with its electrons toward that carbonyl. That's going to push the electrons up to the oxygen, and the product that we get out of that reaction is this one. So this is a tetrahedral intermediate, and what we know about tetrahedral intermediates is that they collapse if they have a good leaving group. And so this tetrahedral intermediate has an oxygen with a negative charge, which we can use to collapse the tetrahedral intermediate. It has an ethoxy group, which is a leaving group. It has the carbon-hydrogen bond that we just made, and it has this phenyl ring. And this carbon-carbon bond and carbon-hydrogen bond are no longer able to act as leaving groups. So the only possible leaving group that I have in this reaction is my ethoxy group. It's the only possible leaving group that I have. So that as this tetrahedral intermediate collapses, I can kick out that ethoxy group, and that gives me this. This structure is an aldehyde. And while we haven't talked about the chemistry of aldehydes quite yet, this aldehyde is a carbonyl, and it will continue to react with the lithium aluminum hydride. So what happens is we have another equivalent of hydride from another aluminum hydride ion that can send one of its hydrides with its electrons towards the carbonyl of that aldehyde, push the electrons up to the oxygen, and what we get in that case is a new tetrahedral intermediate So now when we look at this tetrahedral intermediate, it has no leaving groups. If this oxygen collapses back towards that carbon, I can't kick out the hydrogen or this hydrogen or that phenyl ring, so that this tetrahedral intermediate is stuck. And this is what I have at the end of step 1 in my reaction. Okay, that is what I have at the end of step 1 in my reaction. So here's step 1. The acid workup, as we know, is just there to put protons into the reaction and stop the lithium aluminum hydride from any other reaction so that you can safely work up your reaction. So if I add my acid, in step 2, my oxygen is going to grab a proton from the acid, give the electrons to the oxygen, and I get my final product out of this reaction. My final product is a primary alcohol. And notice at my original carbon of my carbonyl, I now have 2 hydrogens. Each one of those hydrogens came from my aluminum hydride ion. So if I jump back up to reaction number 1, and that's the reaction of the carboxylic acid. The mechanism for the carboxylic acid doesn't go exactly the way that the mechanism for the ester does, but it's okay to think about the reaction mechanism in that way. In truth, this mechanism is a lot more complicated because of the acidity of this proton on the carboxylic acid. That's going to give us a complex that forms between the oxygen and the aluminum, but we don't need to get into that detail in order to understand this particular reaction. So overall, from start to finish, if I treat my carboxylic acid with lithium aluminum hydride, followed by an acid workup, I will do a very similar reaction to what I did below for the esters. That is that I will introduce 2 equivalents of H-, and I will make a primary alcohol out of my reaction. So if I look at the next example, I have a cyclic ester. A cyclic ester is called a lactone. What happens if I treat this lactone with lithium aluminum hydride followed by an acid workup? Pause the video and predict the product for yourself. I hope you were able to think through this reaction. And in order to understand this reaction, we have a cyclic ester, which is called a lactone. This lactone has 1, 2, 3, 4 carbons and an oxygen in that 5-membered ring. So if I treat that lactone with lithium aluminum hydride, what I'm going to do is I'm going to break that lactone right here at that bond. Because during the course of the mechanism, that oxygen of my ester will act as a leaving group. But because this is a lactone, that leaving group can't go too far. So overall, the reaction that I'm going to get out of this reaction will mean that at carbon number 4, I have an alcohol, and it will also mean at carbon number 1, I have an alcohol. So overall, this reaction is going to give me that product there. Another way that we can reduce an ester is with a stoichiometric reagent called Dibol. This reagent is called diisobutyl aluminum hydride, and it looks like this. So that this reagent is going to allow us a stoichiometric amount of hydride. We have 1 aluminum hydrogen bond, and this is a sterically hindered reagent that will allow us to transfer that 1 equivalent of H-. And what makes this reaction unique and this reaction important is that this reduction will stop at the aldehyde. The treatment of an ester with lithium aluminum hydride never stops at the aldehyde. The treatment of the ester with lithium aluminum hydride always goes all the way to the primary alcohol. So this is a unique reaction, and what allows this reaction to work is precise control of your stoichiometry and very low temperatures. If I take my ester and I treat it with Dibol, exactly one equivalent, at a temperature of minus 78 degrees Celsius, and I follow it with an acid workup, I will get an aldehyde and an alcohol out of my reaction. And so the unique piece of this reaction is the aldehyde. There's not a lot of ways that we can stop that reduction at the aldehyde, so that's going to be an important reaction for us. So what's going to happen in this reaction is a little bit like what happened in our hydroboration oxidation reactions. Boron acted as an acceptor of electron density in that reaction, and we transferred hydrogen with its electrons back to the carbon that would have been the most stable carbocation. Aluminum is right below boron on the periodic table, so what can happen in this reaction is that this pi bond can get transferred to the aluminum as a good acceptor of electron density, and at the same time we can send the hydrogen with its electrons back to the carbon of the carbonyl, which would be the carbon that would be our most stable carbocation. That will give us a tetrahedral intermediate where I have my alkyl group, I have my ethoxy group, I have the new hydrogen that I added, and I now have my oxygen that's bonded to my aluminum with my two isobutyl groups, like so. This is a tetrahedral intermediate that will collapse. It will end up kicking off this ethoxide group, and we're not going to go through the rest of the details of the mechanism, but as this tetrahedral intermediate collapses, we'll get the aldehyde. And what's going to allow this reaction to stop at the aldehyde is the fact that we have a complex that forms between that oxygen and that aluminum that will keep my compound from further reacting. As an alternative, if you forget about Dibol as a reagent, or you don't have Dibol when you're working in the lab, you could also apply a two-step strategy to make an aldehyde from an ester. And that would be where you use your strong reducing agent like lithium aluminum hydride, followed by the acid workup, that gives you the primary alcohol. In a second step, you could do an oxidation of a primary alcohol to the aldehyde using PCC.